All right, let's get started here. We talked about the credits. I don't have to repeat all of that. The description was on the website. I'd rather not read it to you, so we're going to go to the next one. And the learning objectives. We're going to talk about why it takes a long time to get hot water to most fixtures in many buildings, and we're going to discuss ways to improve that. We're going to talk about architectural compactness, putting things closer together, in particular the wet rooms and the water heaters that serve them. We've got a bunch of decisions that have to be made to make sure that the performance of faucets and shower heads are high. And we're going to figure out, for those who are interested, of what to do about heat pump water heaters. All right. So, question, do you know anyone who waits a long time to get hot water somewhere in their house, at their job, or in their favorite restaurant? Raise your hands, put it online. Let me see what's going on here. Great. Do you know anyone who's ever run out of hot water? How about any communities that have a you can't build unless you guarantee a long-term supply of water ordinance? We get those in California and the Southwest a lot, just because water is so hard to acquire here. Anyone have a routine they do while waiting for hot water to arrive at their shower or at the kitchen sink or for the dishwasher that you can put in public, discuss in public? People have routines. Anyone who wants instantaneous hot water, right? How about someone who thinks that a tankless water heater is instantaneous? Anyone would like to learn how to get hot water to every fixture, wasting no more than 1 cup waiting for the hot water to arrive? 1 cup is a small definable quantity, and I think it makes sense to aim for that in all buildings we design. So what are we aiming for? People want the water flowing from their showers and faucets to feel right. They want toilets to flush first time every time. They want clean clothes, dishes, and bodies. In summary, they want the service of hot water as efficiently as possible. And the 2 key things they want is hot water now and never run out in their shower. And it doesn't make sense to me to discuss efficiency until the desired service has been provided. People want the service, then we want it to be efficient. So how do we increase customer satisfaction? These are the best practices. This list will come up again at the end. We have to reduce the time to tap, we have to reduce the pressure drop, and we have to install pressure-independent faucet aerators and shower heads to overcome pressure losses we couldn't anticipate. So we're going to discuss these each in turn. The numbers and letters are all there in the text as we go through it. We'll cover all of these. Reduce the distance from the source to the use. The shorter the pipe, the less time it takes, and the smaller the pipe diameter, the less time it takes too. But if you lower flow rates, it takes longer. So my question for you is, how long is too long? How long do you want to wait? I'll start counting. You all raise your hands when you'd like the hot water to get there. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, 6, 1,000, 7, 1,000, 8, 1,000, 9, 1,000, 10. 10 seconds is a long time. Okay? And so the issue is, how do we get hot water to arrive quickly? Water, energy, and time-efficient hot water systems start with deciding how long we want people to wait. The decision on the location of the wet rooms and mechanical rooms is made by the architect. Better floor plans lead to better hot water system performance, and they decrease the residence time in premise plumbing systems, both hot and cold. Premise plumbing residence time has to do with stagnation and clearing it out, getting new disinfectant from municipalities, if that's what's being supplied to you. New water helps with managing pathogens in your plumbing that might be there. So the ideal hot water distribution system has the smallest volume possible from the source of hot water to the fixtures. And sometimes the source is a water heater and sometimes it's a trunk line. And the schematic in the description, we're going to talk about trunks, branches, and twigs today. Twig is not in the plumbing code. It's a term I use because a lot of people I know and I teach don't do plumbing for a living, so I don't want to keep calling them fixture branches, because some codes call them fixture branches and some folks call them something else. We're going to call them trunks, branches, and twigs. Trunks can serve branches and twigs. Branches can serve twigs. Twigs serve one fixture, hot or cold water. Okay? Here's the challenge. How would you do it? Deliver hot water to every hot water fixture, wasting no more energy than we currently waste running water down the drain and wasting no more than 1 cup for hot water to arrive. How would you do it? Turns out we've only found 5 ways. If you want to waste no more than 1 cup while waiting for hot water to arrive, what's the maximum amount of water can be in the pipe that's not usefully hot? Christopher, Rachel, you want to answer the question for me? Darren? Nope. The answer is can't be more than a cup, right, Chris?
That's correct.
But it turns out it can't be that much. It can't even be a cup, but that's the maximum. How close can you get? Well, unless the heater's in the fixture appliance, it's going to be some volume between the pipe and the source, right? In the pipe of the use and the source. And it turns out it takes roughly twice the volume in the pipe before hot water comes out the other end. So we need to decide what's an acceptable time to tap or volume to hot and work backwards. Plumbing from below needs about 5 feet of pipe to get within a cup. Plumbing from down from above needs about 10 feet of pipe. It takes 2 cups unless you can use skinnier pipe. But that's about the buildable dimensions that we can work with. It's hard to get closer. You can do it, but it costs a lot more money to get closer. And so I want to have good practical plumbing that lots of people can implement. Time to tap and volume until hot. Here's the basic math. We talked about more water is in the pipe before it arrives. Hiller measured this in the early 2000s. Yanda Zhang reviewed the data in 2018, and he found that it's somewhere between 1.5 and 2.5 times the volume of water in the pipe comes out before hot water hot enough to shower in, aka 105F, comes out the other end. We're going to call it roughly 2 to 1 for our purposes. So if you want the hot water to arrive within 10 seconds, which is a really long time, as we discussed earlier, there can't be more than 5 seconds of volume between the pipe, the source, and the hot water in the use. Here's a table that allows you to calculate all of this. I use 1 gallon per minute for designing my basic plumbing systems. Why? Most flow rates that people interact with are somewhere below 2.5 gallons per minute. That's a legal US and shower. That's combined flow rate. It's not all hot. The way the valves work, it's about 80% hot, maybe a little less. So if hot water gets there at 1 gallon a minute, if you do the time for 1 gallon a minute, no one will mind if it gets there quicker. And so I use that for the design work. And if you tell me you're going to put in high efficiency fixtures that are, for example, washing your hands in the bathroom, lavatory faucet fixtures at less than 0.5 gallon a minute, I use 0.25 gallons per minute as my sizing rule here, this column. And this shows you in the green that hot water will arrive within less than 10 seconds. All of these give you the choices of being in the green. We want to be in the green, not in the orange and the red. And so in order to get there, you can't have more than 1 cup of water. 8 ounces gives you 8 seconds at 1 gallon a minute. That's the magic number. Okay, and I always do my design at 1 gallon a minute because depending on how you've picked your faucets and your shower heads, they might not be pressure compensating, in which case they might, if you have low pressure, be lower than you think. So this is how I do the design. There's the math for the calculation. I'm not going to spend time on it, but we are going to correct this slide, Christopher, for finishing all this up. The length of pipe that holds 8 ounces of water. This is a table for your reference. Our best practice has been for many years, no more than 2 cups from the source to the use. Pennsylvania tends to have this thing called basements. Certainly in a lot of single family residential stuff, you end up with a basement. If you have a basement, which we don't get here in California, we get slabs. You can typically get within 1 cup to every fixture that's above the basement. If you put fixtures in the basement, you're plumbing from above down and you need the 2 cups to get down the wall. Why 2 cups? Because 1/2-inch plumbing is typically the minimum diameter that's allowed in the plumbing code. And because of concerns over lack of pressure or lack of available pressure at the fixture, people don't like to use 3/8 tubing. I will tell you, however, there's some good YouTube stuff now on the web from Allison Bales showing how he renovated his house to use 1/4-inch tubing. And everything is working just fine. Okay. Now we're going to talk about the distance between the wet rooms and the water heater. That's the second piece. So this is all piece of this distance problem. We have this definition of things called a hot water system rectangle. It's the box surrounding the water heater and all of the fixtures. If this water heater in the garage had been closer to the wall, the corner of the wall, which is where you would have put a storage water heater in our case, then I would have drawn the rectangle much closer because the plumbing wall isn't at the far end of the bathtub. The plumbing wall is here where the faucets and the sinks and the shower valve are. We only account where the valves have to go. In this case, it shows that approximately 67% of this floor area of the whole dwelling is related to the hot water system. There's a relationship for the logical worst case. If you have a single-story dwelling and the water heater's in one corner, the worst case would be the furthest fixtures in the diagonally opposite corner. For 2 stories, it's 50% of the floor area, 3 stories, etc. Here's the largest hot water system rectangle we've seen so far in a study we've done of California housing about 8 or 9 years ago now. If you notice, the water heater is here in the far side of a large 3-car garage. Okay. They managed to put a nice big covered entryway in a big courtyard, and they have a guest suite out over here served by these water heaters. And the owner's suite is back here, and the kitchen is all the way over here. And in order to get to that sink, they usually run the water on this wall because they know where the foundation is going to be when they build it, and they have to get under it to run to the kitchen sink. Might be over here, but it's almost 155% of the floor of the house because it goes outside the dwelling to find all the fixtures. The best one story so far is this. I met the fellow who used to be a Habitat for Humanity home builder at a conference in California. It must be over a decade ago now. And this was the house that he was building. It's pretty typical. It's Habitat for Humanity, so it's not, it's not a big house, but this is the typical size range and the layout. The water heater was here in the garage, and the furthest fixture was over here. Kitchen is over here. You can see how the bathroom groups are all spread out. We had this conversation about distance, and he goes away and comes back a year later, no communication in the middle, and he's got it down to this. Water heater is now close to the laundry room. The kitchen sink is over here. The bathrooms are back to back instead of spread out. And if you count the outside dimensions of the bathroom, you end up with a rectangle about 15% of the floor area. But the fact of the matter is that you're only supposed to count where the walls of the plumbing are. These are the plumbing walls. Water heaters move. We'll fix that too. But you see that that's the plumbing wall that has to be counted. And so we're down at 4%. I'd say the guy solved the problem in the first shot. He comes back a year later at 2.5%. He's tightened everything up, moved the laundry room to here, the kitchen over here. So now we have an I-beam relationship rather than a rectangle. And all the plumbing runs in this wall, not to the ceiling and down. It runs horizontally in the middle of the wall. So you lose all the vertical height as the distances as well. And then finally, this is the third iteration. We are now down to 0.8%, less than 1% of the floor area is dedicated to the hot water distribution system. And it's all in this wall. And there's a water heater hanging over one of the 2 toilets that are back to back. It's a tankless water heater. There's plenty of space for that. And the plumbing goes sideways. It's really very, very efficient. So the idea is a logic problem. How do you get things close together? How do you create mechanical cores? We're talking about plumbing cores here, but the principles apply to all of it. And center doesn't have to be exactly center. So the best 2 stories so far, you actually own a piece of this building. This is at the National Institute of Standards and Technology in Gaithersburg, Maryland. And the water heaters in the basement and all of the plumbing fixtures for this very nice, generous house is all in 12% of the total floor area of the house. This is a great solution.
20-minute mark, Gary.
Thank you. These are common distribution layouts with the potential to be water, energy, and time efficient. If you have standard trunk and branch, either single trunk or two trunk systems, it's random. Time to tap is inconsistent, and the ability to be potential to be water, energy, and time efficient is relatively low. It's maybe retrofittable, but it's not intended to be particularly highly water and energy and time efficient. The high case is the if you have a small recirculation loop and short branches or twigs to the fixtures, it's low with a long loop and continuous pumping. If you want it to be energy efficient, you have to run the pump minimally, and the best strategy we've ever found is to use it on demand. I know now when I plan to take my next shower, I suspect most of you do too, but I'm certain I know how many of you know. You turn on the tap and wait for a minute or so for hot water to arrive. Why would you want to run a pump 24 hours a day for that special minute that happens for the shower once or twice or 3 times a day per household? You're spending a lot of energy on that question. I don't like to do that. Their strategies for this are pretty well straightforward. Timers get out of whack all the time, and they run when we're actually using the hot water, which we don't need to do. We need to run the pumps just before we want hot water. And this one is another high potential. You have compact distribution piping. As long as the twigs are short and the water heaters are close, life is good. If you have long twigs, you have low ability to be water, energy, and time efficient. All right, we're going to right size the plumbing. That's the second piece of the puzzle. Which pipe sizing method do you use? I don't know. You're in Pennsylvania, many of you. So I'm assuming you use the Pennsylvania Plumbing Code. Go ahead, Christopher.
Or the IRC. That's a pretty prevalent source.
Right. Okay. So the IRC makes a lot of sense. I work on these codes, so I'm familiar with many of them. And the IRC is using a method that's been in place since the 1940s. So that's when the first research was done in the 1930s that was published in 1940 by a fellow named Roy Hunter, who worked at the predecessor to NIST, where he did a predictive model that says the probability of simultaneous demand is high or low, but it depends on what fixtures might be on at the same time. And it's all based on data from the 1930s and early 1940s. Well, nothing flushes or flows that way. And most occupancies do not act like being at a theater with lines during intermission, right? We don't wait in line much anymore in our dwellings. We might if we go to a stadium, but in the airport, but not at home mostly. So the Uniform Plumbing Code, actually IAPMO started with WESTAND, the Water Efficiency Standard Committee, where one of the services I serve on, one of the committees I serve on. In about 2010, we started working on a change. And the water demand calculators was published for the first time in 2017. We're now on version 2.2, and it allows you to toggle between a single family and a multifamily residence, and you can basically input the number of fixtures you need on each relevant branch of the whole building. You press run and you get an answer that tells you how many fixtures are in the calc and what the peak demand looks like. This is a class all by itself on how to use it. I will tell you there's huge benefits. And here's what happens. This is for a 92 unit apartment building in, I think it's in Seattle. If you reduce the time to depth, you increase customer satisfaction by right sizing the piping and the rest of the plumbing, the water heater and the meter, because all of that's possible. You get first cost reductions somewhere between $600 and $1,200 in first cost savings per apartment. 100 unit apartment building, that's like serious money. And then operational savings change because you don't need as big a water main and as big a meter. All of that's part of the built-in costs. And we're not counting the energy saving from waiting less for hot water to arrive, nor are we counting sewer costs for the extra savings. So, reducing the pressure drop in pipe and fittings. That's the next piece. Well, what is it? What is the pressure drop in modern pipe and fittings? Well, we don't use steel pipe. That's what's in the tables. And so it turns out that the work that we use for all of our design work was published in 1941 by Freeman. But he was the son of the guy who did the work in 1892 for steel pipe and threaded and flange fittings. So about 15 years ago, I started looking into this question so we could figure out what we're doing with modern fittings. I set up a lab in Downey, California. That was in 2015, so that's a decade ago. We moved the lab to Arcata some years later, and this is what it looks like in the Arcata lab. That lab is actually now in Wisconsin, Madison, Wisconsin. And so we're able to measure pressure, we record pressure, we're measuring flow rate, and we have a test rig we set up stable pressure tanks, and we record the data. I'm going to show you the results. This is the setup that we use. On the first slide, you can see the discharge. In the middle, you can see how we've set up a long run of straight pipe. We typically do a rectangular spiral. This is a rectangular spiral with bend supports rather than 90-degree, hard 90-degree elbows. This is showing you 90-degree in copper. This is showing a long loop with T's in it. And this is a coil of PEX pipe, all of which are normal configurations that should be tested. Why does it matter? Modern fittings are either, if you're copper or PEX, if you're copper, your fittings are all on the outside. Notice that copper, PEX, and CPVC all share the same outside dimension, which is why SharkBite type fittings work. There is cold expansion fittings, and there's insert, crimp, or press fittings. And you notice what happens to the inside diameter. It gets much smaller with the different fitting types. Insert fittings have the potential to dramatically reduce available pressure by increasing pressure loss as you go through a fitting. So the target flow rates are this. In order to do our experiments, we had to set up an idea to get a pressure loss at a given velocity. We can't measure velocity directly easily. We can measure flow rate. So we measured flow rates. We got to these, and we'd run the test for 60 seconds, and we'd produce the results. These are results of 60-second tests at each of these velocities for different materials and different elbows. This is all copper, elbows and T's, and you can see the spread. It goes from, I'm picking here on the end at 10 feet per second, which is not a normal dimension and not a normal velocity to use. It's less than 0.5 PSI per fitting. On the right-hand side, it's also copper, and it's compared to what's the scale for PEX fittings. So this is 0.5 compared to 7. Copper fittings have inherently low pressure loss. So I want to assume the target flow rate the customer wants is 3 gallons a minute, which is a toilet or a bathtub or a washing machine. They don't really know what the plumbing is. They just want to make sure they get the flow rate. That's at 4 feet per second. And the pressure drop is on the order of 0.05 PSI per fitting. When I switch to PVC, I still want the same flow rate, right? Which is somewhere in the middle here. Call it about 5 PSI, 5 feet per second. I'm around 0.2 PSI per fitting. And again, this is the scale on the right-hand side to PEX, which means that CPVC fittings are also relatively low. But it's gone up by 4 times. Now we split out in half-inch PEX between the T's and the couplings on one side and the elbows on the other. You'll notice there's groupings here. This is based on the fitting technology more than anything else. Some fittings have low pressure loss, some have high pressure loss. And you notice carefully here on the right, there's one fitting that's essentially flat. It's as though there's no difference than the straight pipe would be. Anyone want to hazard a guess which fitting that is? Anyway, while you're thinking about that, at 5.5 feet per second, our pressure loss is somewhere between 5.5 is here. It's around 2 PSI. So we went from 0.05 to 0.2 to 2 for the same desired flow rate. Customer has no idea what that's going to be because the house has already been built. Building's already done. So we decided to see what the fittings were compared to, we wanted to see if we could bend pipe and how we could make it act as though it's straight. So we did straight pipe, curved pipe, coiled pipe, and bend supported pipe, all of which are easy to set up and test. And if you look carefully, at 5.5 feet per second, the pressure loss is around 0.12 PSI per foot, which is what we needed for the PEX. Okay? And this is pressure loss per foot. They're all about the same. Notice that the bend supports and the coils and the straight pipe are very, very similar out in here in normal flow rates. It's very amazing that they're that close. Bend supports make a big difference. If you want to learn nothing else, that's what you need to do for 90-degree elbows. We did the same test for 3/8-inch copper and PEX, but the pressure losses are higher because the inside diameter is smaller. Now we're at the 7 feet per second in copper to get the same 3 gallons a minute. I still want my 3 gallons a minute, right? That's the same thing. We're after the same point. And at 7 gallons at 3 gallons a minute, I'm at 10 feet per second in PEX, which is higher than most codes want us to go. So we've measured it. And again, we did the straight pipe comparisons, and at 10 feet per second, which is what we need for PEX, we're at 0.6 PSI per foot. In elevation terms, it's 0.43 PSI per foot of height as you go up. The pressure loss for that at that flow rate, at that velocity, is higher than the pressure loss per foot of elevation. If I wanted to be similar, I'd be down here at 8 feet per second. This is showing the different types of fittings that are available to us. We want bend supports, or what I call swoops. It's trademarked because I have a trademark for that shape in plumbing. Anyway, we want to minimize the number of fittings, particularly sharp 90-degree elbows. And when we're building with flexible tubing, we should not have any. It's just not necessary. When you get to the mechanical room, switch materials and make it easier to have less pressure loss. All right. Now we're going to reduce the pressure drop in the faucets and the shower valves. We talked about what to do for the pipe and fittings. We're going to talk about tub shower and shower valves. Does anybody remember doing the shower dance? I do. You know, when you're in the shower, when you had the old two-handled shower valves and someone flushed the toilet, you paid a lot of attention because if you didn't get out of the way, you'd get scalded. That's gone away with modern tub shower valves, which have anti-scald features built into them, and it's a requirement in most codes that they be used, and it's really hard to find valves that don't have them. So I went to the store and got a whole selection of valves that are very typically used in new residential construction at price points that are also typical for the trim kits. Turns out you can have lots of trim kits with the same valve, so what matters for our purposes is the valve inside the wall. This is what you see if you look close. You can see that, you know, this describes cold on one side, hot on the other, up and down for the, up for the shower, down for the tub. This is a side view look. This is a side view look. You can see a big hole here going down, and you have this one here. This is actually going back up again, I guess it is. This one is showing you what it looks like on the downside. The big hole goes to the tub, and the skinny one is when you pull the diverter, it goes back up the skinny little hole. Well, it's a pretty small hole, and look how that's not very big either, right? Here's looking at a side view of another valve. You can see this little skinny tube. I'm going to tell you the inside diameter of that hole in this device is on the order of 3/16 of an inch. How did I measure it? I took a drill bit, found the one that fit, and it's 3/16 of an inch. But the pipe feeding it, you will see, is a 1/2 inch pipe. But the diverter going to the shower is 3/16. What do you think the pressure loss is through here? It's a huge restrictor. So what we're trying to do is to see how the valve is built to determine whether it's contributing a lot or a little to pressure loss at your shower head. Okay, let's make this work again. There we are. So we use the same test rig, but set it up a little differently. You can see the two valves. This is deciding whether it's going for the tub part or this is the shower part or the tub part. This is the tub. You can see the valve is set so that we can get it right in the middle. And we want the flow rate to be as maximum as going to be. It's roughly 50-50. We used cold water only for this test because the viscosity of cold water is greater than hot water. And so we want the friction loss to be high, not exactly what it's going to be in use because we don't know what the mix will be. And so then we measure what comes out of the valve, and we put it through our pressure and flow rate stuff, and we can measure the difference. So we did this in 1/2 gallon per minute increments of flow, all the way up to 5 GPM, or when I ran out of available pressure in our rig. We only had about 50 PSI to give away, so that we just stopped at some point in the experiment. And if you lose 50 PSI through the valve, you pretty much are in trouble anyway, because you're only allowed to start with 80 PSI at the building entrance, and 50 PSI through a shower valve is a lot. So we were able to measure this through the shower portion of the valve at California legal flow rates, which are 1.8 GPM. That's the WaterSense value as well. You end up with about, what is that, almost 14 PSI coming through the valve range at the worst, and the best is around 4 PSI. So it varies between the valves by a lot. That's a 3 times variation. And you say if we go at 2.5 gallons per minute, which is US legal, it varies from about 0.8 to 24, 25, 26, somewhere in there, almost 26 PSI. That's a huge variation in range. And which one do you want in your house? I want the one that's the least. Well, this one here is a shower only valve, and so is the black dash dotted line here. These are shower only valves. But if you're doing tub shower valves, you have to start with the green line. Well, the variation is still almost 2 to 1. Okay. 2.5 to 1, not 3. So it's a big variation. There's one manufacturer in here that has 2 valves with different pressure losses. I hope to God they ended up with the one with the best, least. Okay. So you want to select carefully to make sure you have to know what the residual pressure is coming out of the valve. The code only stipulates what the valve pressure must be before it enters the valve. And we want tubs to fill quickly, say faster than 2.5 gallons per minute, but the pressure drop through the tub spouts more than doubles from the lowest to highest as you go out here to the right. So flow rates are rarely more than 3.5 gallons a minute in most new buildings and most of the available commonly used tub shower valves, not 5.5. Again, you want to select carefully. All right, now we're going to get to the fun part. How do you fix all these problems because you don't know what actually got built? You're going to install pressure independent faucet aerators and shower heads. So what happens? There's fixed orifice, which means when you have high pressure, you have high flow, and low pressure, you have low flow. And before 2000, practically all fixtures and fixture fittings and appliances, all of the shower valves, everything we're used to was a hole with pressure behind it. Okay, which is why people complained when the federal government regulated the flow rates for faucets and shower heads, particularly for shower heads, people complain. You're intimately involved with what comes out. And so people would take out the aerator in order to give them more flow. Okay. What they're doing is you have high pressure, you have X pressure and you want more flow. And that's how you would solve that problem. But the company that makes the insides for almost every US shower and head and faucet aerator makes adjustable orifices. They're pressure compensating orifices. And you get almost exactly the same flow rate for pressures above 20 to 25 PSI. And these are available today in 90% of all shower heads and many faucets. Okay. Here's what happens. The gray line is for your shower head. We're going to assume everything is at 2 gallons a minute. All right. And the pressure at which the flow rates are rated is 80 PSI for shower heads. Follow the gray line. If you only have 40 PSI, you're going to get 1.4 gallons per minute. And if you only have 20 PSI, you're going to get 1 gallon a minute. And if you thought you bought 2 gallons a minute and you ended up with 1, you're going to be very unhappy and you will say so. But if you put a pressure compensating flow regulator inside the shower valve, which you can see is this rubber O-ring inside the blue plastic ring, this O-ring gets compresses when the pressure is high and relaxes when the pressure is less, and it opens up the holes that are around the ring, and you get the same flow. And in this case, you get the same flow rate down to 40 PSI, and you get 85% of what you would have gotten instead of 50% when the pressure is only 20. Okay, all good. Let's look at what happens for faucet aerators. Same flow rate. We picked it for this for a reason to make it easy, but for reasons that escape me, shower heads are rated at 80 and faucets are rated at 60. Aren't they like 4 feet, 5 feet apart in most bathrooms? You know, one's up and one's down, but they're not far away from each other. It seemed a little silly to me. I'm going to suggest that the difference is because it's the committee and they were drinking and smoking back in the 60s and 70s, and I won't say what. Mathematically, it makes sense, but from a customer satisfaction point of view, it doesn't make sense to do it differently. Anyway, follow the gray line. You at half the rated pressure at 30, you'd get 1.4 gallons a minute. At 15 PSI, you get 1 gallon a minute. You're not happy. If you put in a single core pressure compensating flow regulator, like you did for the shower, you'll be up here. But if you could get the gold standard, you'd be here, which is like 95% of the rated flow down to 20 PSI. I'd say that's pretty good. Pretty good. That's really good. So on the right-hand side, you can see these color-coded these color-coded aerators for faucets are at are fixed orifice. The single core you can see here and here are all one O-ring, and if you look carefully, you'll see the little holes around it. And this one's got dual core. Guess what? All faucet flow regulators are now available in dual core. Manufacturer told me that a year ago. I was so excited I wanted to hug them. I've been asking for this for 20 years. Since I knew it was possible, I've known. So since 2010 at the late early, so 15 years I've been asking for this. It makes sense. Why would you give away customer satisfaction? It gets rid of all the complaints you'll have about all this stuff, and it gives you what you thought you bought, or awfully darn close to it for all pressures available at most faucets. So,
15 minutes left, Gary.
thank you. Let's move on. Let's talk about air source heat pump water heaters. What's different about heat pump water heaters? Where do they get their energy from? They get it from the air, right? They use electricity to, as we do with outdoor heat pumps, to convert the electric energy, modify the air by changing its temperature, and they store the heat in the water instead of the space. They have slower recovery rates than we're used to with gas water heaters, and if they have to, when the air temperatures or the air temperatures are very low, you're going to use resistance energy. We want to minimize resistance. So how do you ensure enough hot water? Well, there's a whole variety of sizes of compressor size, burners, and elements. In the case here is we want, what do we get? Well, most heat pump water heaters are small compressors, which means you need larger tanks to match the loads of the daily use in the building. And so we end up with things on the left, but it's a continuum. If I could get bigger compressors, I'd need smaller tanks. The question is matching heat rates and tank size to the need you've got in the building. So the biggest thing we have to do is to manage cold air, because the exhaust air can be below the dew point. And if you blow exhaust air below the dew point around inside the building's envelope, as we teach in most of the building science classes, that can cause serious problems like moisture damage and mold. So we want to prevent moisture issues. You don't want to trap exhaust air in a small enclosed space. We want to raise the cold exhaust air above the dew point as quick as we can. If we're going to have ductwork, you need to make sure it's insulated and vapor sealed so moisture doesn't condense on or in the duct. All right, we want to provide sufficient warm air for the energy side so that there's enough energy in the air to give you a high COP. You want the performance to be above a 3.0 COP. That's sort of the minimum that is of interest to most of us who work on the energy side. And you need a thermal resource that's big enough. And the question is, how is the thermal resource going to get to the air used by the heat pump water heater? So let's look at a problem. Unitary heat pump water heaters have different locations of intakes and exhausts. The one on the left is a top intake, a side exhaust. The second one is a top intake and the other side exhaust. There's the one in the middle with a top intake and a rear exhaust. Then there's one with a top intake and a top exhaust. And there's a side intake and a top exhaust. Two side intakes and a top exhaust. So there's different variations. These are the logical choices available. I don't care which brand it is. This is a logic problem that has to be sorted out. And if you look carefully, the various fittings and connections are in different places than are standard for typical water heaters. We now have to think harder about installing them, either in new construction or in retrofit. So a typical water heater location are the ones on the left. I'm guessing that there's a lot of basements where you are, where water heaters get put. Sometimes there's a mechanical room in the basement. They go there. Some buildings end up with water heaters in a closet. California, we like to do things with putting water heaters in garages because it's the best, most available space in most new construction. Older houses had closets in the middle of the hallway, typically. So we have to make sure we ensure the safe discharge of the cold air in the most confined location. We're going to look at closets. Okay. So this is an example of a rear exhaust and a top. It doesn't matter where the air intake is. It can be on either of the sides at the top. It doesn't matter. But this is a rear exhaust. What we want to do is to make sure that the air gets out of the closet. You need space to make the turn at the back. behind the water heater, which means you need a deep closet. It turns out in this case, you need almost a 4 foot deep by 4 foot wide closet to meet all the rules of service and maintenance. And these green things on the front over here are, these are filter grills. This is a standard HVAC filter grill. Okay. Why a filter grill? I want to be able to open it up and take the filter out and replace it periodically. Why 2-inch pleated? Because there's lots of surface area. Why do I need a lot? Because I want to protect the compressor and the coils inside the heat pump. That the, the filter that comes with them is very, very small, and it's got bypasses around it, so it lets air with dust buddies in it get to the coil. So this is showing you a way to solve the small closet problem. This is another example with a side exhaust. I'm not going to spend a lot of time on this one. It's the same thing. You can study them later. The first case had 2 doors, if you look carefully, because it was a 4 foot wide, but we don't make 4 foot wide doors very much. They don't fit in hallways. So we have to have a 2-fold door. And here we have a one door will do the opening. It'll be okay. And we can have a slightly smaller closet, but currently the best case we have is if we have a top exhaust. Because if we have a top exhaust, I can put the water heater as close to the wall as I'm allowed to do for service and access. I've made it 3 inches here, maybe get even closer, which means we can solve the smallest closet problems correctly. Air in doesn't matter as much as exhaust out does. We're using an HVAC supply register, a good one. We're blowing air sideways and up. Why? We don't want it to blow on people. We want it to mix with the room. If you've got mechanical equipment for heating and air co-located in the same basic space as the heat pump, I think we should be working on ways to integrate the exhaust air of the heat pump into the return of the HVAC system. We'll cover that in Q&A. There's some low-risk strategies. Big rooms with access to warm air works great, but you must discharge the cold air away from surfaces and mix it thoroughly before it becomes intake air and before it hits a surface. In small areas with limited access, you have to duct the air out into a larger space to mix it before it becomes back with intake. And then we want to use large MERV 13 filters. We know all about that from our HVAC work. The water heating industry doesn't know much about them. And it turns out that we have found a product available to us in the market already by a company that makes air-to-air heat exchangers. This is exactly the temperature ranges of conditions we're interested in. And this shows you some of the vapor tight and insulated ductwork that's purchasable for us today. It's a great idea. So in summary, here are the best practices for hot water systems. We want to deliver increased customer satisfaction. If we do that, people will tend to like the result. We want to reduce the time to tap by reducing the distance and, if possible, in both cases, the diameter of the pipe to be right-sized in terms with modern information. We want to reduce the pressure drop in the pipe and fittings and the faucets and the shower valves. We install pressure-independent faucet aerators and shower heads because we don't know all the pressure losses that are built into the building. And we give first dibs on available pressure to the customer by putting these in. And if we're going to install heat pump water heaters, air source heat pump water heaters, they need to be right-sized. They need to get enough warm air, and we have to manage the exhaust to protect the health and safety of the building and the occupants and increase efficiency. And with that, given human nature, I think it's our job to provide the infrastructure that supports efficient behaviors. Questions? Back to you, Christopher.
Well, Gary, first of all, before we jump to this one question, I just want to thank you again for taking the time out of your day to hop on a webinar for us over here on the East Coast here in Pennsylvania, although hot water moves the same no matter where you are. So thank you again very, very much.